Howdy, I'm Ethan Edgington.
And I'm Matthew Cadman.
And together, we built a cognitive software-defined radio. One of the biggest problems with radios is that interference often prevents them from receiving their desired signals.
So our solution is to apply AI in order to extract information about those desired signals, enabling automated, interference-resistant reception. Here is an overview of our system. On the left is a clean signal transmitter, and in the middle is a transmitter that adds interference in order to generate a distorted signal.
We can then receive those distorted signals from your standard Windows computer using a custom receiver application. This app has built-in AI capabilities that allows you to detect and listen to a signal from the push of a button. We'll start by opening the Cognitive Pluto SDR application, which is custom-made using MATLAB. Simply connect your add-on Pluto SDR to your device via a micro USB cable, and the application will automatically detect it and begin receiving. Inside the application, there are a few controls off to the left. Here, you can adjust the center frequency of the application to anywhere within the SDR's limitations. You can also adjust the bandwidth. Before we explore the other controls, let's talk about the AI. The Convolutional Neural Network, or CNN, is a kind of artificial intelligence trained to find patterns in data. It utilizes a common mathematical concept known as convolution to filter large masses of data into recognizable patterns. Our architecture inputs the IQ samples received by the Pluto SDR and passes them through several layers, each one more specific than the last. Once the IQ data has passed through each layer, the CNN draws decision boundaries, which is shown as the plane in the middle of this figure. Back in our receiver app, let's say there's a transmission we want to listen to. We don't know if it's an AM or FM signal, so we'll use our AI to detect it automatically. The auto bandpass button will detect the most prominent signal currently being received and set our bandpass filter to lock in on it. As you can see, the AI detected an FM signal. Let's take a listen. So, how accurate is it? Overall, the model holds up very well with an average training score of almost 99%. This confusion matrix shows us it's slightly more likely to predict FM than AM, but with a success rate that high, those numbers make a negligible difference. One alternate CNN architecture was trained using spectrograms to detect AM and FM signals. While the best results produced a smaller file size for the AI model, it required a greater use of processing power while receiving and provided a less accurate result.
So in summary, we built, tuned, and characterized 2 test antennas. We built a test transmitter that sends audio using several common modulation types, and we built a user-friendly transmitter control interface.
We also created a standalone executable that can receive signals from your add-on Pluto SDR. It has the ability to control the listening region and play back the demodulated audio there. And finally, a convolutional neural network that can classify real-time AM and FM signals. Once again, my name is Ethan Edgington.
And I'm Matthew Cadman.
And this has been the Cognitive Software Defined Radio.